Welcome, everyone. For today's prep, we're going to look at some properties of the natural log function and really any of our common log functions, but we're going to specifically look at them for natural log. And we're going to see how we can use these special properties to sometimes simplify our function down in order to make it easier to differentiate. And then this is going to lead up to our last major differentiation technique. And it's called logarithmic differentiation. So we'll probably see this in class. But let's get to our natural log properties. So what are the properties of our log functions? Now we have these nice algebraic properties. So we have, let x and y be positive numbers. So again, we can't plug negative numbers into the log function. And b here can be any number. All right. So we have three properties that we're going to look at. The first one tells us what we can do when we have multiplication of two terms inside of a log function. So here we have natural log of x times y. So it's not explicitly written, but there's a multiplication symbol hidden or right there in the middle. So we have natural log of x times y. And what this property tells us is that we can kind of break this single natural log term up into two separate log terms. So we get the natural log of just the x plus the natural log of just the y. So what happens in this case is we have multiplication that's inside, and it gets converted into addition outside. It's really nice. Multiplication's kind of a more complicated operation. So what we have here is this algebraic property of our log function that essentially is converting multiplication into addition. And there's a similar property for division. So in the next property, we have natural log of x divided by y. And essentially what happens is this property converts it into the natural log of x, the natural log of whatever was on top of our fraction, minus the natural log of what was ever in the bottom of the fraction. And again, in this case, this log property is converting division. So we have this division sign here inside of our log function, and it gets converted into subtraction. So again, kind of an easier operation. So we have inside division, that's inside the natural log, and it gets converted into subtraction outside of the natural log. So kind of nice. And then we have one more property here that tells us what we can do with exponents. So if we have an exponent inside of a natural log function like this, so we have natural log of x raised to the power b, well, what we can do is we can essentially take that exponent and we can move it out and put it in front of the natural log. Now, this isn't derivative or anything. This is just a property of the natural log function. So again, what we have here is we have our x, and then it's the x term is being raised to the power b. And so this property essentially allows us to take that exponent, and the exponent gets converted into multiplication. So what we have here is inside we have an exponent, and outside it becomes multiplication. So again, exponent is kind of having an exponent, having a power function is kind of like repeated multiplication. So an exponent is more complicated than multiplication. So when we have an exponent inside the log function, it gets converted into multiplication outside the log function. So again, kind of nice, kind of helpful. And let's see how we can use these. So let's look at our first example, and we're going to use these properties to help us calculate the derivative of this function. So before we do any derivatives, we're going to rewrite this log function using these algebraic properties. So when we look at this function, we got the natural log kind of on the outside here. And then we have all this stuff that's inside of it. So we're going to work with all this stuff. So the first thing we want to just kind of characterize, ultimately, what do we have here? So the main operation going on inside this log function, it's division. So we can rewrite that division as subtraction. So we can take the natural log of just the top function and subtract off the natural log of just the bottom function. And while we're at it, I'm going to rewrite this square root as a power function, kind of our usual technique. So raised to the 1/2. So all we've done is we've done the natural log of the top function, the natural log of whatever was in the denominator of our fraction, and we're subtracting now. So we're using that property that essentially converts division into subtraction. Okay, so this first term, really nothing more we can do. There's no multiplication, there's no division, there's no exponents in there. We're kind of stuck. This is as far as we're going to simplify this one. Now the second one, we can actually do a little bit more with, because when we look at this, we have this x minus 2, and that whole thing is being raised to an exponent. So we can use our exponent property for this second natural log term. So we can take this exponent, this power, and we can move it out in front of the natural log. Again, we're not doing any derivatives yet. We're just using the algebraic properties of the natural log function to rewrite everything. So if we do that, the first natural log term is going to stay the same. And then let's bring that that 1/2, and we're going to put it in front. So we'll have minus 1/2, and then natural log of just the x minus 2. So again, all of this is just rewriting using our log properties. So for the second one, we rewrote the exponent as constant multiplication. All right, so now we've simplified our log expression down as far as we go. So again, this one, we can't simplify this any further because there's no multiplication in there, there's no division, and there's no kind of surrounding exponent. So the log function doesn't really simplify if we have addition or subtraction inside of the log function. That's kind of where we stop. All right, so at this point, this is as good as we're going to get it. So now we're ready to do the derivative. So our function's called f, so let's call our derivative f prime. And we're just going to go through and differentiate each of these individual log terms. So for the first one, that first natural log term we differentiate. So now this is a composite function, so we have our outer log function and then we have our stuff inside of it. So we're going to do the reciprocal of the stuff that's inside and then multiply by the derivative of that stuff that's inside. So this is chain rule. And then we go on to our next term. We have a minus 1/2, so that's just a constant, so that's just going to stay there in front. And then this natural log term is a composite function, so we're going to differentiate our way through the log function. So we do the reciprocal of everything that's inside the log function, so 1 over x minus 2. And then we're going to multiply by the derivative of x minus 2. So again, another chain rule here. And then we just finish it off. So the derivative of x plus 1 is just 1, and then the derivative of x minus 2 is just 1. So we end up, when we simplify this down, we end up with 1 over x plus 1, our first fraction, and then minus 1/2 times 1 over x minus 2. And there we go. We got our derivative. And just notice, this made the derivative process a lot easier. If we didn't simplify our function down with these log properties, first we would have had to do the reciprocal of everything inside to differentiate our way through the log function. Then we would have had to use quotient rule. And then we would have had to use power rule when we differentiated that square root term. So we just would have, it would have taken, we could have done it, but it would have been more complicated. And there would have been, more terms in our answer. So using these log properties really simplified our function down to a point where the derivative wasn't too bad. So what we're going to see in class is how we can use these log properties with a technique which we call logarithmic differentiation to calculate derivatives for things like this, where this isn't a regular function that we've seen before. This is not a power function. It's not an exponential function. It's kind of unusual because the variable x shows up in a few different places. It shows in the base term, and then it shows up in the exponent term. So this is kind of an unusual type function, and we're going to, using a log to simplify this down, is going to help us out. So we'll see that in class. Bye-bye.